Okay, thanks a lot for a very nice introduction. So I'm going to tell you a tale of quantum gravity. It's really a tale of two theories. So the first theory I'll be talking about is Einstein's theory of general relativity. Now, I'm sure you all heard about curved space-time, black holes, other really amazing things in general relativity. And the other theory I'll be talking about, it's quantum field theory. And that's the theory of elementary particle physics. So let's say this would be some kind of a scattering process of electrons, and there's a photon, and there's quarks and gluons. And we generally describe it by these types of diagrams. These are the founding fathers of quantum field theory. Quantum electrodynamics is what they discovered. And what this lecture is going to be about is taking Einstein's general relativity and trying to put it together with quantum field theory. So first, we're going to talk about Yang-Mills theory. So that's a theory. 3 of the 4 known forces in nature are described by what are called gauge theory. So this thing that was claimed to be the best one is a dead one. Let's try that again. Always have a backup plan. Okay. So 3 of the known forces of nature, they're described by what are called gauge theories. We, of course, know about electromagnetism. There's a founding father, Maxwell. And then there's the strong nuclear force, QCD. That, of course, that David won the Nobel Prize, of course. The weak nuclear force. And together, these 2 are described by what are called Yang-Mills gauge theory. They're generalizations of electromagnetism. There's Yang and Mills. And we have here the elementary particles. So there's the quarks, the leptons, the electron, neutrinos. There's 3 generations. The force carriers, there's the photon, the gluon, the Z boson, the W boson. Now, let's have a look at gravity. Well, that looks different. It's not based on a Yang-Mills theory. It's based on a geometric theory, curved space-time. And then it has all these marvelous concepts you don't really find in the other theories, such as black holes. And when you when you look at the quantum field theory, then what happens is, first you find gravitons. Those are analogous to photons. Okay, no one has actually discovered a graviton, but we're quite sure they do exist in the same way that photons exist. But very quickly, you come across infinities, ill-defined problems in the theory, and these types of, call them untamed infinities, they don't occur in this Yang-Mills theory. There you have infinities, but we know very well how to deal with them. Now, this problem, in fact, these infinities, I'll be talking more about that later in the lecture, but that's actually a problem that's solved through string theory. So that's the most popular way to deal with this and other problems in quantum gravity. But I'm not going to be talking about that. I'll be talking about a more traditional approach, just trying to take gravity and putting it together with quantum field theory. And then just try to understand what kind of issues happen and what's known about these untamed infinities. So quantum field theory, well, at least if we do expansions in h bar, that's Planck's constant, then we usually describe quantum field theory through these Feynman diagrams. So these are pictures, but they represent algebra. Say this would be gluons interacting to give quarks and W bosons, and this would be a correction, a loop correction. So there's a more complicated contribution. And this is all part of quantum field theory. The more loops you see, the more complicated it gets, and the more quantum-like it gets, the more contributions that go like Planck's constant. Now, gravity, it's similar. You can draw these same pictures. It's just a lot more complicated. Now, the quantum field theory, it's really the most precise theory that we know by a long, long shot. And the favorite example that people like to use about quantum field theory, about its precision, is something called the anomalous magnetic moment of the electron. And what that is, it's the magnetic moment of the electron compared to its spin. And when you compare the theoretical prediction against experimental measurement, it's accurate to 1 part in a billion. Unbelievable. Absolutely unbelievable. The first calculation done by Schwinger. Okay, he didn't use Feynman diagrams, actually, but anyway, it's done by Schwinger. And then Kinoshita devoted his life to making these theoretical predictions. Like I say, 1 part in a billion. Extremely complicated calculations. You do it, and it works 1 part in a billion. There's no other theory like that. Now, this is using quantum electrodynamics. The theory I will be talking about will be quantum chromodynamics and its connection to gravity. We call that also Yang-Mills theory. You sometimes use that interchangeably. Okay, and let's see what people said about quantum field theory of gravity. So you've probably read Brian Greene's book or some other popular book, and you see some statement, Einstein's theory of general relativity is incompatible with quantum field theory. Now, the experts in the audience know that that's a little bit of a silly statement, but nevertheless, people say that. But this statement is usually based on another statement, which is more precise. It says, all quantum field theories of gravity have untamed infinities, and that's known as the non-renormalizability problem of gravity. Right. Okay. So where do these statements come from? And then the more important question, are these statements true? These are statements people repeat, but just because they get repeated doesn't mean that they're true. Now let's have a look at infinities. What do I mean by infinities? Well, I literally mean you add something up or do an integral and you get infinity. By the way, if you have an iPhone, don't do this. Don't Google it. 1 plus 2 plus 3 plus 4. Don't Google that, because you'll find the answer is minus a 12th, not infinity. So that'll contradict what I just said. But anyway, it's naively infinity. Actually, it's true. Google it. Now, normally we don't think about sums, but really integrals. And this would be a good example. This is a logarithm. You do this integral, you get infinity. And in quantum field theory, we deal with infinities all the time. Standard practice. So this would be a very typical integral, a more complicated one than that, but a very typical integral of quantum field theory, and the answer is infinity. This infinity is actually our friend. That's part of what's called a renormalizable theory. We know exactly how to deal with it, some redefinition of coupling constants, and then the infinities are swept away. They're our friends, not a problem. But then there is another set of infinities when you get to call them unhappy theories like gravity, and those infinities are not so easy to deal with, and we call that non-renormalizable. And just to give you a little taste, this is David's comment about the technical subject. When you look at let's say, a gravity Feynman diagram, so this is actually a very complicated one, but it's actually an interesting one. This would be 1, 2, 3, 4, 5 loops. So that's an interesting one for us. And you look at the integrals that you get, comparing Einstein gravity against Yang-Mills theory, then what you find is the integrals that you have, there's more of these momenta, these are momenta, and then you're integrating over them, more upstairs, and then you find integrals that are very badly behaved. And it's actually connected to the fact that Newton's constant, this is Newton's constant, carries dimensions. And it's directly connected to the fact that the integrals you find have a very bad behavior as these momenta go off to infinity. And that's the non-renormalizability problem. And there's absolutely no doubt about this, that the Feynman diagrams of quantum gravity are poorly behaved. That is, you could say, proven. But you have to worry about something, and this is the loophole, and this is a loophole everybody knows. is that there might be cancellation between the diagrams, that there's something special going on, a hidden cancellation. And when I say a hidden cancellation, I don't mean hidden from the theory. I mean hidden from us humans, that we can't see it. But there's just some cancellation. It's just our description in terms of Feynman diagrams. It makes it hard to see what's going on. The question is, are we sure there must be bad infinities if you add up all the diagrams? How do people know? Of course, my answer is going to be people don't know, but we'll get to that. Now, we're going to look at a type of theory called supergravity, and that involves this idea of supersymmetry. It's actually kind of a cool word, super. It's actually a technical word when you use the word super. It means a symmetry between forces and matter, between bosons and fermions. So, and what supergravity is, it takes this idea of supersymmetry and it combines it with gravity. So the idea is that, let's say you have a graviton, then what supersymmetry postulates is that there's a particle called a gravitino, which is a partner, a superpartner of the graviton. Now, we're pretty certain that the graviton exists. We're not so certain the gravitino exists, but on the other hand, it's just a theoretical toy model to try to understand properties of gravity. And there are some good reasons why we like these theories, which I'll explain in just a second. But first, let's talk about different types of theory. We're going to talk about a theory called n equals 8 supergravity. And what that refers to is that for the graviton, there's 8 superpartners. That's where this name n equals 8. There's actually, this theory has 256 particles. It's quite a complicated theory in some sense, but the particles all are related to each other through the supersymmetry. And this is the maximum you can have and still have a gravity theory. And what supersymmetry does, the reason why people like it a lot and why people studied it in great detail in the 70s and 80s was because it helps tame the infinities. What happens is the bosons come generally with one sign, like a plus sign, fermions with a minus sign, and these infinities tend to cancel. Okay? And in fact, in the 70s and 80s, this idea of supergravity, it was really seen as the most promising means for unifying gravity with the other forces until string theory came into prominence. And we're going to be looking a lot at this n equals 8 supergravity. So that's Einstein gravity plus 254 other particles. And the reason to focus on n equals 8 supergravity, why I'll be talking about this theory a lot, is because the more supersymmetry you have, the better the non-renormalizability problem will be. So it's a good theory to be looking at if you're interested in understanding how it behaves at high energies. Okay? And the other reason is when you have a lot of symmetry, then usually it's easier. The problems become simpler. Okay? Now, what did people say in the 80s? So this was just as they were dropping supergravity and saying, well, supergravity isn't working, we need something else. So in 1982, for example, you see here's a quote that's actually kind of interesting. If certain patterns that emerge should persist in the higher orders of perturbation theory, that means higher and higher loops, n equals 8 supergravity in 4 dimensions will have ultraviolet divergences starting at 3 loops. I want you to notice the careful wording, right? They didn't say, we know the answer, because they didn't know the answer, because precisely this question of some kind of hidden cancellations or that there's something going on that they don't know about. But they said, as far as we can see, it's going to have problems starting at 3 loops. And then here's another one. I like this quote a lot. Okay, it is therefore likely that all supergravity theories will diverge at 3 loops in 4 dimensions. That includes, of course, n equals 8 supergravity. And then they say, this is the great part, the final word on these issues may have to await further explicit calculations. And that's exactly what we're going to do. So we're going to go old-fashioned, right? We're going to actually do the calculation, not pontificate. On the other hand, we're going to be using modern, newfangled ideas to do the calculations. Okay, here's an amusing quote. There's Hawking. Okay, so in 1994, he said, it is not clear that general relativity, when combined with various other fields in supergravity theory, cannot give a sensible quantum theory. And then reports of the death of supergravity are an exaggeration. I think he stole that from Mark Twain. But anyway, one year, everyone believed that supergravity was finite. The next year, the fashion changed, and everybody said that supergravity was bound to have divergences, even though none had actually been found. Which is true. Now you say, okay, but why didn't people find it? Well, let's have a look at what happens if you try to find it. So if you look at a three-loop Feynman diagram of gravity, I'm just talking about one diagram, never mind the billions of other diagrams. Let's pick this one. And you just do a little bit of arithmetic to try to figure out how many terms of algebra or how many terms in the expression for this diagram. You'll find something ridiculous, 10 to the 20th. It can't be done. It's impossible. Or if you go all the way to 5 loops, which will play an important role later, we're talking about 10 to the 31 terms. That happens to be more terms than there are atoms in an average graduate student's brain. It doesn't fit. You can't do the calculation. Now, of course, if there are some experts here, they might complain about the way I'm counting, but it doesn't make any difference. You can count this any way you want. The conclusion is the same. Calculations to settle this seemed utterly hopeless, and then this question just seemed destined for the dustbin of undecidable questions. Let's compare that to the modern way of doing things. Quite a bit better. 3 loops, 10 terms. So sometimes as a stunt at summer schools, I just work it out on the blackboard. Okay, it takes a little while, an hour and a half, but it fits on a blackboard, it gets done in an hour and a half. Okay, and when you get to 5 loops, that's already pretty complicated, and we've been having some technical troubles with it, but it's definitely within reach. Okay, now to understand more about how we attack quantum gravity, then we could have a look first at scattering amplitudes. Okay, so the scattering of elementary particles, that's described by Feynman diagrams, and that's something absolutely fundamental to our understanding our ability to unravel the microscopic laws of nature. And of course, this is being done most prominently at CERN, 27-kilometer ring. There's the Atlas detector. And this actually is kind of fascinating to talk more about this. In fact, there's a program running right now at the KITP on LHC physics, precision LHC physics. But unfortunately, I'm not going to say anything about that because my mother did teach me one thing, which is don't cram too many topics into one lecture. So I'm not going to speak about that. But anyway, let's talk about Feynman diagrams, the complexity of Feynman diagrams. So back in 1948, Julian Schwinger, he computed this anomalous magnetic moment of the electron, the first correction, or the first contribution to the anomalous magnetic moment, and it was a 3-point diagram. So you use 1, 2, 3 legs on the outside. We go 60 years later, and then we look at the same type of calculation, and then we say, what can we do 60 years later with Feynman diagrams? We're talking about 2 or 3 legs more than Schwinger could do. And you go, wait a second, how can that be true? Schwinger didn't have supercomputers, right? What's going on? Well, let's have a look at that and try to understand what the problem is. Let's look at a relatively simple process. So this would be something that you'd have to calculate to understand how protons scatter off each other and the gluons inside the proton, how they scatter. Call it a Five-Gluon process. So that's a Feynman diagram calculation. And by the way, this is relatively simple. This is kind of child's play by today's standards. But still, it's kind of instructive. Let's just follow the textbooks. Okay, maybe older textbooks. Modern textbooks are getting a little more sophisticated. But if we follow textbooks from 10 years ago, this is what you get. There's no structure. It's very complicated. If you kind of blow up, see what's in there. These are momenta. These are called polarization vectors. So that has to do with the spin state. Is it circular polarized this way or that way? But anyway, you get some very messy combination. Actually, this is a tiny part of the answer. That's about a 25th of the answer. On the other hand, if you understand the physics, the basic states, the circular polarization, we call them maybe plus minus helicity, then using what's sometimes called Chinese magic, in honor of these people, then you get much simpler expressions with a structure. I'm not going to explain exactly what these symbols mean, but this page and the previous page contain the same information. Actually, this is only a 25th of it. This is the much simpler expression. So what this teaches you is by looking at things the right way, all of a sudden things become very simple and they have a certain structure that you can try to exploit. Now, these are the simplest diagrams. These are the tree level. They're called trees. When you stick in the loops like this, this is a loop diagram. I'm not going to talk about the diagram. I'm just going to pick one term. There's thousands of terms. I'll just pick one term. I happen to pick the most complicated one. And you get an integral. There's some integral that you get. Now, of course, by modern standards, this is not complicated. We have computer programs to deal with this. But if you do the calculation, you will find a catastrophe. Okay, now, this catastrophe here, imagine what happens if you start combining it with the previous catastrophe, like this one, right? Where you have lots and lots of external legs, right? Lots and lots of particles on the outside. Then things really get bad. Okay, and that's the basic reason why we can't do that much better than Schwinger, even with our computers, if we use standard Feynman diagrams. Now, what's the problem with the Feynman diagrams? You can actually track it down to something very basic. Einstein's relation. So everybody knows E equals mc squared. I assume that's the most famous formula of any formula in physics. Now, this formula, it's for zero momentum. We physicists, we use a slightly different formula where we include the momentum. So this is really the correct Einstein relation. This is, when this is satisfied, which every physical particle satisfies, we call it on-shell. This is an on-shell relation. And when we look at the Feynman diagrams, then the instructions are to integrate over all energy momenta, and that violates Einstein's relation. Now, that probably sounds like a bad thing. You don't want to violate an Einstein relation. I wouldn't do that. And in fact, that's the source of the problem. What happens is the individual diagrams, they're not physically meaningful. And if you can try to figure out a way of doing things that you don't violate Einstein's relation, then you can do better. And there's something we call modern unitarity method, on-shell recursion. And those have been very helpful ways of looking at scattering amplitudes. Now let's compare what happens with Feynman diagrams of gravity compared to gauge theory. So that's the Yang-Mills theory. And very quickly, you realize that there's trouble with Einstein gravity in its complexity. So I was complaining about complexity in gauge theory just a minute ago, but gravity makes gauge theory look like child's play. And part of the problem has to do with the number of interactions you can have. So you have one graviton splitting into two, or one into three, or one into four, and so on and so forth. And you can have infinitely many such interactions. And these interactions get more and more complicated. This theory, it stops at what's called a 4-point interaction. The Yang-Mills theory stops at 4 points. And certainly, it looks more complicated. But let me make that a little clearer, what I mean by more complicated. So this is Yang-Mills theory, 3 gluons. And you can see it looks a little complicated, but it's not terrible. And then we compare it to gravity. This thing is out of control. And in fact, it's much worse than you think it is, because there's like slick ideas. Like this actually is 6 terms. And this is 3 terms, and so on and so forth. And then there's more terms. There's a little symbol there that says it's even a bigger mess. It's about 100 terms. Now, if you're a clever graduate student and your professor shows you this 3 graviton vertex and says, well, I want you to do a calculation, the clever graduate student should say, oh, that's very nice, but I'm going to go work on a different problem. The better way of looking at things is don't violate Einstein relation. So if you use Einstein's relation, you can clean that up. And we look at Yang-Mills theory, and you see, well, okay, not too much happened. It's still pretty simple. But look what happens to Einstein gravity. See, this looks just like that. Looks like 2 copies. Okay? And that's not an accident. That's actually something very profound. It might look like an accident. And in fact, it turns out that all the information of Einstein gravity, as long as we're thinking about scattering of gravitons, it's all contained right here. Okay? And in fact, gravity is just as simple as gauge theory. That's the correct statement. Gravity is not more complicated than gauge theory. And we're going to exploit that. But first I want to show you something really weird. Okay, I want to call it duality between color and kinematics. Okay, what do I mean by color? Well, color is the analogy of electric charge. So in quantum chromodynamics, we don't have electric charge, but we have color charge, and that's controlled by some kind of matrix. FABC, that's some kind of matrix. But think of it like electric charge. Okay, and then there's this kinematic part. That's momenta. That's a 4 momentum. That's momenta. Okay, and one thing for sure, if I told you electric charge is like momenta, you'll say, what the hell are you talking about? Okay, but that's basically what I'm going to say. I'm going to say that there's a relationship, a duality. There's an equivalence between them. And what do I mean by that? Well, these color charges and these color factors, these are called color factors, associated with this diagram or this diagram or this diagram, is some color factor that comes from these matrices. And it satisfies an identity that every graduate student learns. It's called the Jacobi identity. And it says that the color charge or color factor of this diagram is equal to the color of this diagram minus that one. Okay? But there's another relation, and for those of you who are more sophisticated, run home, check your quantum field theory book, work this out. Okay? And you'll find that the numerators satisfy this kinematic numerator. There's some factors associated with this. So I'll call that a kinematic numerator coming from here. And it satisfies exactly the same relation. It's algebraically identical. And that's what I mean by duality. And you'll say, well, that's pretty weird. Who really cares? Well, actually, it's even worse than that. This thing maybe you shouldn't care so much about, but it's even stranger that even experts don't really understand this, not certainly fully understand where it comes from. But this is actually the key to gravity, this little observation. Because it turns out that if you line things up so that you take your Yang-Mills theory, you take a set of diagrams, and you arrange things so that this duality holds, so the algebra, the algebra of the color and the algebra of this kinematic numerator, there's something called Feynman denominators. Never mind, that's something that's very generic, not so interesting for purposes of my talk here. But if you line things up so that these two satisfy the same types of identities, these Jacobi identities, like here, these types of Jacobi identities, then it's magic. If I want gravity, all I do is I take this formula, I take this color factor, I replace it with another kinematic numerator. I replace with a second copy. We call this double copy construction. This gives me Einstein gravity. It's like magic. If I want to calculate in this theory, I actually calculate in the simpler theory. It's great fun. And in fact, there's something very profound here, because we can start with Einstein gravity. We work this out, and we find these kinematic numerators, and they're identical to what you find in the Yang-Mills theory. Where did that come from? Well, nobody knows the answer to that question, but it's definitely something very useful and something very profound. And what's better is it works at loop level. We don't have a proof of that. That's why I say conjecture. But never mind whether we have a proof. We can still use it. Now, you can guess that it's true, and then you check that the answer is correct. So we use it as an awesome calculational tool. So when we want multi-loop gravity, the way we do it is we do gauge theory, which is far simpler than gravity, and then we just make a replacement. Color factor goes to a numerator factor. It's like magic. Now, it's not like magic. It is magic. Actually, wouldn't it be really cool if you could do this for every possible solution of Einstein gravity? So where would you start if you want to investigate that? Well, obviously, the coolest place possible, you start with black holes. And in fact, that's where my friends started. What they found is what's called a Schwarzschild black hole. That's kind of a boring black hole. It's not spinning. It's just sitting there. And they found that there's a relationship, I call it a double copy relationship, to electric charges. And here's some of the formulas from their paper, but you can see this K. So this K, there's two copies here, one copy there. So what they explain is Schwarzschild black hole, that's the boring black hole. It's like a point charge, but two copies of it. That's really cool. And in fact, they've generalized this now, all sorts of cases, including even radiation from an accelerating black hole. Now, it might be possible to extend this to more general cases, maybe even gravity waves from colliding black holes, which I think has generated some excitement. I don't know if you can do that, but I do know people are certainly thinking about that now. And what I really hope is we can write a really great formula that looks like this. Einstein is two copies of Yang and Mills. Okay, what are we going to do with this? Well, we're going to look at it just disappeared. Well, there's supposed to be a diagram there. It disappeared at the last minute. I swear it was there about an hour ago. Anyway, there's a three-loop diagram. Here, I'll draw it over here. Three-loop diagram. This is a three-loop diagram. I don't know if you can see that. Whoops, maybe you can't see that. Anyway, it's three-loop diagram sitting there. And anyway, back in 1987, 2007, we were pretty sure that what people said back in the 80s couldn't be correct. So we just did the calculation. And the answer is it's finite, contrary to previous, people had said in the 80s. Now, when you do a calculation like that, you probably know what's going to happen. People will say, oh, that's a great calculation you did, but you know you're going to have trouble at the next loop order. And indeed, that's what happened. In 2009, there was a paper, Bossard, Howe, and Stell, and they said, their abstract of the paper, in particular, the ... is whatever methods they used, something about ectoplasm, but never mind, suggests that maximal supergravity is likely to diverge at 4 loops in d equals 5 and at 5 loops in d equals 4. And basically, they're going to say you're going to have trouble. Now, of course, in a case like that, what are you going to do? You're going to make a bet. In fact, that's the bottle of wine that my friend Kelly Stell put up. But we have the tools to collect the bottle of wine. Once you have a bet, you work pretty hard. So we decided to do the calculation. That was in 2010, and it's a little bit complicated. It's like 50 diagrams you have to do. Now, my graduate student at the time, he said, I am not shaving until we finish the calculation. Now that he's more experienced, he knows never to say that. But anyway, you can tell from the length of his beard how long the calculation took. Maybe that's 8 months. But anyway, this was just before we finished. So we took a photo because we knew it was close. And this is the day we finished. Looking kind of stressed out here, isn't he? Looking pretty relaxed over there. Anyway, the answer is I got the bottle of wine. It's very useful. I used it for my 20th wedding anniversary. Now, you know what's going to happen if you do a calculation like that. People will say, well, that's a great calculation you guys did. But, you know, you're going to have trouble starting at 5 loops. But by now, a lot of people got really interested in this because it looked like something was going on, something unusual. And a lot of people started working on it. And in some time, they were able to explain all our previous results. Every calculation we had done was explained by some kind of standard argument, just refined. They worked on it and polished their arguments. And then after a while, they could explain everything that we had done. And then they predicted that we'll start having trouble at 5 loops, and by 7 loops, it's going to diverge. Now, a reasonable person would conclude that this n equals 8 supergravity almost certainly diverges at 7 loops in 4 dimensions. So d is the space-time dimension. But when I say 4 dimensions, I mean space and time. And in fact, these people did a lot of work and looked at different theories. Okay, n equals 8 supergravity should diverge in 4 dimensions. N equals 8 supergravity should diverge at 5 loops in 24/5 dimension. Don't worry about that. We're theorists. We can work in any dimension we please, even dimensions that don't make any sense, but never mind. And then also supergravity theories with fewer supersymmetries. It's called n equals 4 supergravity, half the supersymmetry, n equals 5. They made these very nice predictions. Now, 7 loops is out of reach. 5 loops is giving us some heartburn, but we could do 3 loops, we could do 4 loops. Now, I think you might know what the answer is. Oh, by the way, here's one of our competitors. Actually, look at the whiteboard. He's obviously ahead of us. Huh, that's weird. Hold on. There's a bug. I don't believe it. You know the missing diagram? Came back. How do you like that? Okay. Yeah, it's that diagram I lost before. It was actually there. Just there's a bug somewhere in the PowerPoint. Okay, anyway, we're back in business. Okay, so me being an unreasonable person, decided it was a good opportunity to make some bets. So first bet I have, at 5 loops in 24/5 dimension, does n equals 8 supergravity diverge? Okay, I'm from California, so I put up California wine. My friend Kelly Stell, unfortunately, he lives in England, so he put up some English wine. And he says it will diverge. I say it won't diverge. Okay, I also made another bet with David Gross. David wouldn't have anything to do with 24/5. That's 7 loops. Anyway, we got evenly matched here on the California wine. Okay, so let's find out what the answers are. So we could calculate n equals 4 supergravity at 3 loops. That's no problem. That was no problem for us. We just decided to sit down and do the calculation. It's a bit complicated. This table shows you contributions from individual diagrams. Actually, these 1 over epsilons represent infinities. So there's like a table of infinities and done in some way. And it looks a little bit complicated, but you add everything up, you get 0. And you can take a photo with your iPhone and then add it up, you'll see it does add up to 0. There are no infinities. So the main thing I have to say about that, it's sure a pity we didn't bet on this theory. I actually wanted to, but by the time I decided it was time to bet, we already knew the answer. So that wouldn't have been fair. Anyway, there's no standard explanation for this, despite a very strong attempt by our friends to do that. And this phenomenon, we've given it a name, enhanced cancellations. In fact, it turns out that I don't think it's possible that there will be a standard explanation for a very specific reason that has to do with this name. And we've also looked at other theories, this n equals 5 supergravity. Okay, this is not something you try at home. This is a professional grade, industrial strength software that we needed help from some Russians. That's when you get really serious. C++. It's about 1 billion terms if you're curious. But we really wanted to know what the answer was. So we did the calculation, and yeah, it's exactly what you might have expected. Another example of enhanced cancellations. Once again, it's a pity we didn't bet on this theory. I would have gotten that English wine. Now, there are some examples of theories. N equals 4 supergravity. It does actually have a divergence at 4 loops, but it turns out it's kind of a weird infinity. It has something to do with what's called a quantum anomaly. It's certainly not generic. Even pure gravity, something that people thought they understood very well, it's pretty strange how it works. It's kind of a curious story that when where you think there's infinities, you don't find them. Okay, and then some places you do find them, but then they're kind of weird. They're not what you expect. So what are the conclusions? Well, the first one is reports of the death of supergravity are an exaggeration. So supergravity is back from the dead twice. First, it died in the 80s. And then it died again just a few years ago when everybody said, look, we understand that everything that's going to happen. No, it's not really true. There's these enhanced cancellations that happen, which we've proven in a number of cases. Okay, I don't know if this is going to lead to some kind of satisfactory description of nature. That's a pretty tall order. But at least people are studying supergravity. And I certainly hope I convinced you that we uncovered some interesting things along the way of trying to understand supergravity theories. If you want some further reading, there's some things you can look at, including our Scientific American article. Okay, thank you.
Questions? They're canceling infinities. Just give them a minute. Yeah, here we go.
Can you define UV? What does the UV term,
Yeah, I'm sorry about that. Before I came here, I said I got to define ultraviolet. And then I forgot to do it. I just mean high energy. So in the integral, when the momentum and energy goes very high, and the term it's just a term that physicists use, that ultraviolet light is beyond, it's high energy. So that just means high energy. It's just a weird word we use. Thanks.
I have a question that relates to the history of physics. Maybe when you find an unreasonable symmetry that one thing seems to look exactly like the other thing, and I'm thinking now of your color charge factors and your kinematic variables. Someone like Einstein would have said, well, maybe they are exactly the same thing from another point of view. Is there some possibility that there's a higher perspective where you're actually looking at exactly the same thing, but we just have different language for it now?
Yes, I think there is. There's theories called Kaluza-Klein theories, where you work in higher dimensions, and then you do what's called dimensional reduction. And then from that vantage point, you can understand how these Yang-Mills theories are connected to the gravity theory. And I think through that vantage point, you can gain some insight about what's going on. So there's definitely a way of thinking about it that way. Well, the duality, well, oh, yeah. Basically that there's some interpretation that comes from string theory. The answer is maybe. There's certainly people who are writing papers about color kinematics, duality, and string theory. Oliver Schlotterer and Mafra are people to look at. But the actual relationship is a little bit obscure still. It's not. I mean, you're definitely right that there's a lot to learn from string theory from this point of view, but it's not as if though all of a sudden you understand everything.
I kind of have two things. One, we just talked that supersymmetry is having difficulty at the LHC. Is this in any way relates, like if supersymmetry is not verified? And the other thing is, I guess there's nothing mathematicians can really sink their teeth in here with terms of theorems and so on.
Sorry. Well, maybe let me answer the first question, and then we'll get to the second one. Whether the LHC discovers supersymmetry or not, it's somewhat independent of what we're talking about here, because we're using supersymmetry as a mathematical tool, as a theoretical tool to help us understand gravity, to understand quantum gravity. We would do that one way or the other, whether the LHC discovers supersymmetry. Of course, if the LHC did discover supersymmetry, we would probably be working a lot harder on supersymmetry. But there's no direct connection. It's a different physical question.
Although your gravitinos, you're a result of supersymmetry thinking.
Right, but let's assume that the LHC does not discover supersymmetry. It will not stop us from using supersymmetry as a theoretical tool, as a mathematical tool for being able to understand quantum gravity. It helps us tremendously, independent of whether the LHC discovers it or not. Okay? But like I say, if the LHC did discover supersymmetry, I think more of us would be working on supersymmetry.
Michael.
I have a comment for Lars, really. On the way home, my wife is going to say to me, as she usually does, well, what did we learn today? And all I can say to Lars is, I'm going to have a tough time on the way home.
Well, okay. Well, I can recommend what you do is you Google me and you Google TED, T-E-D, okay, and you look that up and you find something. You'll find a video there, and you tell her to watch the video. Okay? And the one thing that the punchline of that video I can tell you is clever ideas are going to beat a computer anytime. Because the way we calculate, here's the punchline. If you want, like, what do you tell your wife? Okay, you're going to say, there's this stuff people are trying to understand in quantum gravity, and where'd it go? There you go. You can't possibly do the calculation ever with all the world's computers. And all you need is some good idea, some way of relating the thing that's so complicated to something that's much simpler. And then you can do the calculation. Right. That's also true.
So I have eventually learned to wrap my head around multiple dimensions by cheating and assuming some are wrapped up tiny. How does one wrap his head around 24/5 dimension? And is it ultimately a mathematical
that's
trick?
really simple.
Is it simple? Okay.
Yeah. You don't wrap your head around it. That's the first thing you do. The second thing you do, it's just some trickery. And in fact, this is exactly why I could not get David Gross to bet on 24/5 dimension. He said, doesn't make any sense. It's just some trickery that we do to help us work. But you should not think of it as literally 24/5 dimension.
So we all learned early on that in quantum mechanics, we should look at small systems to see quantum effects. If you looked at really big systems with lots of particles, it kind of behaved classically. What about quantum gravity? Is there any experimental situation where we should look for quantum effects, or is that never going to be observable?
Well, early universe is probably the only place that you can really look for quantum effects. Maybe you heard about the bicep fiasco. There it is, quantum gravity. Of course, it hasn't been found, but the potential is there. That's the place to look.
All right, well, thank you very much, Zvi. Remind everybody, we do have refreshments out by the courtyard, so please feel free. And see you on May 4th at Soho.